Hi, welcome to AP Chemistry. This is Mrs. Dahlberg, and our computer kind of glitched in the last video, and so we were kind of stranded in the middle of 2007, number 2, and we had already worked or talked about this problem, and we were just discussing the points for this problem. So you had 1 point for using the correct molar mass, or in other words, finding the number of moles of the neon, the full neon, and not the number of moles of the neon 22. This is just a percentage of the actual sample. The next part, and that's recognizing that in neon, 90.5% will be the other isotope. So if you have 12.55 grams, you have both of those in there. And so this has to be used, the average atomic mass, because it contains both. You earn 1 point for the correct fraction of neon 22. So if you used your answer from the previous part to calculate the number or percentage of those atoms, and then 1 point for the correct number of atoms. Okay, the next part of this problem says that for neon, there's an emission spectrum at 4.34 times 10 to the 14th. Calculate the wavelength in nanometers of light that corresponds to this line. And so if we look at that, if you're given a frequency, you have two choices. You can use the speed of light equation, or you can use the energy equation with Planck's constant. In this case, we're given the frequency and we want the wavelength. And so this one is not too useful to us in this situation, but the other one is. And so if we know the frequency, we can put that here. And if we know the speed of light, we will get, substituting in our values, we will get a wavelength of 690 nanometers. Now, this one is converted to nanometers because it asks for the wavelength in nanometers. Occasionally, if it asks for the specific units, you will not get credit if you don't. Sometimes, if you put this answer in meters, you will get credit. So, in the upper atmosphere, ozone, or O3, decomposes as they absorb UV radiation, as shown by this equation. So we look at this equation, UV light will break down the ozone in the ozone layer into O2 and an oxygen radical. So we have O3 absorbing a photon with a frequency of 1 times 10 to the minus, or to the 15th seconds to the minus 1, or hertz. How much energy in joules does the O3 molecule absorb per photon? Okay, so if we're talking energy and we're given frequency, now we want to use that equation I talked about earlier with Planck's constant in it. And so if we set that up and we plug in Planck's constant and the frequency given here, we would get 6.63 times 10 to the minus 19 joules per photon. Now, part 2 of that says the minimum energy needed to break an oxygen-oxygen bond is 387 kilojoules per mole. Does a photon with this frequency have enough energy to break this bond? Support your answer with a calculation. Okay, and so the difference in these two kind of are the units. So if you look at that, this is in kilojoules per mole, and this is in joules per photon. And so if you convert it so we can look at apples to apples, you can literally just compare the numbers. And so if we take that first number, if you have 6.63 times 10 to the 1 minus 19 joules per photon, you can convert that to a mole of photons. And then you can convert joules to kilojoules. There's 1,000 joules in 1 kilojoule, and you get the number 399. And now all you have to do is compare this number to the 387. And if we do that, we see that that number's greater. So yes, it can break the bond. You have enough energy. If this number were less than 387, we wouldn't be able to. So 1 point for calculating the energy, another point for comparing the bond energies. If this answer is wrong, like for example, if you calculated it and it was 200, you would put that here and say this is less than 387, therefore the bond cannot be broken. You could still earn this second point for comparing the bond energies correctly. Moving on to 2015, write the electron configuration for a zinc atom in the ground state. So if we write the electron configuration for a zinc atom in the ground state, many times it says write the complete electron configuration, in which this is the only acceptable answer. But the noble gas configuration is here as well because it doesn't in this particular problem. And so in the valence electrons, we have 4s2 and 3d10. The next part, it says, from which sublevel are electrons removed when zinc atom in the ground state is oxidized? So when something is oxidized, it loses electrons. So we want to know, where does it lose electrons from? Which orbitals? And so if you look at zinc, it loses its electrons from its outer shell or the 4s2 electrons. Don't forget these 3d10 are inner electrons. Okay, 2016, number 1, we have an enthalpy for two different salts, and we're given information about their radius. And so if you look at lithium, it has a radius, or the lithium ion rather, has a radius of 76, and sodium has a radius of 102, and we want to write the complete, see that word complete, electron configuration for the sodium ion in the ground state. And so we look at that, we have 1s2, 2s2, 2p6. The thing that was there, if you wrote the sodium atom, you might have written 3s1, but this is the electron that was removed when it formed a +1 ion. So now you have to explain, why is the sodium atom larger than the lithium ion? And a good explanation will talk about the fact that the sodium ion are in a higher principal energy level, or they have one more shell than the lithium ions, and the electrons are farther from the nucleus, despite the fact that sodium also has more protons. But if you talk about principal energy levels or number of shells, you would get C, part C right. Okay, so at the bottom here we have a representation of a crystal of lithium chloride, and we have to identify the ions by writing the formulas in the box. And so you have this nice picture of a crystal lattice, and you have some obviously large ones and obviously small ones. And so this one is pointing at the large one, this one is pointing at the small one. And so if we had just the atoms, we know that we could probably figure something out. But let's look at lithium. When lithium becomes lithium ion, it loses an electron and it becomes smaller. The opposite is true from chlorine going to chlorine negative ion. It gains an electron, so it becomes bigger. And so if you had this in your table, you were right. The bigger one is the chloride ion, the smaller one is the lithium ion. Let me grab our periodic table. We could probably guess that looking at, here's lithium. It's in this energy level. When it loses one electron, it only has one shell of electrons. It's very small. The chloride ion has 3 filled shells when it gains one electron. So that accounts for the huge size difference there. Okay, y'all have a great day, and that is the end of our free response practice. I hope it helps on the test.